surfaces, different elliptical and parabolic surfaces. So 1 second. Here. Nope. Okay, this is planes. So it should be fairly close. Sorry. Okay, here. Okay, I missed it again. Sorry. Here. Okay, so the first surface that we're going to look at is the ellipse. So quadratic surfaces. So the first surface that they tell us about is the ellipse, and we have seen different versions of the ellipse, but this is the ellipsoid in general. So if we're given a surface and we want to understand what's going on, it's always important to trace different planes of the surface. So if you have the following equation, x, okay, so you have the following equation, x over a squared plus y over b squared plus z over c squared is equal to 1. Okay, so we can start by thinking about what happens when we set z is equal to 0. So if we are in the xy coordinate system, xyz, sorry. So if we're in the xyz coordinate system, then when z over here is 0, we would have x over a squared plus y over b squared is equal to 1. So that's when z is equal to 0. So you think about this line getting smushed, and that would be an ellipse over here. So it looks something like this. And this point over here would be the point A. So sorry, A 0, 0. 0, 0. Okay, whatever, but I'm just going to write A. So it's the point where x is equal to A. So maybe I'll just write that, x is equal to A. That's over here. This point over here is when y is equal to b. Okay, now and this over here is in the other side. So this equation just became x squared over a, sorry, x over a squared plus y over b squared is equal to 1 minus z0 over c squared. Okay, so now when we have this, 1 second. So far, does this make sense? Okay. So when we have this, then as my z0 gets bigger and bigger, this entire thing gets bigger, so this whole thing gets smaller. And this happens when z0 gets smaller too, because this is positive. So if when z0 gets bigger, you're higher on this, higher up over here, maybe you're at 1. So sorry, yeah, 1 would be fine. So that would be 1 minus 1 over c squared, whatever that number is, and then you would have an ellipse there with that radius. So, but it would be smaller. So you might have an ellipse a little higher. So you would have something like this with that radius. Let me try to redraw it. Okay. And then at some point when z0 is equal to c, you're just going to get a point because your radius is going to be 0. And the same thing happens in this direction. Now, this is one of the directions. This is the z direction. We can also write the same exact thing for y0. So we can say, oh, x over a squared plus z over c squared is equal to 1 minus y0 over b squared.
We can't see where you just wrote that. Oh, never mind.
Yeah, my computer apparently is doing too many things, so it's having trouble with this. But okay, if we write something out like this, then we're now doing the exact same thing, but now in the xz plane. So here's x, here's z, that's the plane. So we're going to have one ellipse, and it's going to hit the x-axis at A, same place as before, and it's going to hit the z-axis at C. So this over here is z is equal to c. And then we'll go around like this. And then as we increase or decrease our y0, this is positive, so we get the exact same thing. Smaller and smaller ellipses until we hit a point. And in this direction too. And then we hit a point. Okay, and then the same exact thing happens in the x direction. So if we did this in the x direction, we would get y over b squared plus z over c squared is equal to 1. Sorry. Yeah, 1 minus x0 over a squared. Okay, so now if we did this, then we would have the exact same thing as before, but now we're in the yz, so this is yz. So now we're having ellipses going like this. Like that. And again, this is CB, so this is y is equal to b, and this is c is equal to z. And then as we continue, these ellipses get smaller and smaller in the as x0 gets bigger and smaller. Any questions about this? So this is how we can see that this gives you an ellipsoid. Okay. So they're basically doing the same exact thing. Like you can see, this is the plane z is equal to 0, where we would create a trace. And they ask us to find the traces of this ellipsoid. So we can have the different ellipses that we get when we set the y, z, and x to 0. So this is when we set z is equal to 0. So then we get one ellipse. And that's the blue one in the figure, so that would be this one, that blue ellipse over there. When we set x is equal to 0, we get this over here, so it's an ellipse 7 in the y direction, 6 in the z direction. So that's this. Yeah, that's this over here, that ellipse over there, 7 and 9. And then when we set xz, when we're looking at the xz direction, so we set y is equal to 0, so that's when y is 0. And then we are looking at the red one over here and the ellipses that we get out of those. So those would be ellipses over there. And then they show you how those ellipses fill in the picture. Any questions about that? Okay. So now let's go on to the hyperboloid, and we have two types, of one sheet and of two sheets. So the first equation that we want to look at is this equation over here. So that is the equation x squared x over a squared plus y over b squared is equal to z over c squared plus 1. That's the first equation. One second. Yep, perfect. And this one over here, this is what makes it connected to a hyperbola. So if we have So let's first do the easy part. Let's first think about when the z is fixed. So if you look at the equation where z is fixed, you're looking at the equation x over a squared plus y over b squared is equal to z 0 over c squared plus 1. And then if we're looking at our x, y, and z coordinates, and let's just wait for a second. Okay, then if we're looking at the x, y, and z coordinates, we are going to we're going to have ellipses again, because this is going to be our radius, this is going to be our ellipse, and as we go up and down over here, this is going to get bigger, and the smallest situation is when this is 0. When z0 is 0, so this is 0, so it would be 1. So the smallest ellipse that we get in this situation is here, at z is equal to 0, and that ellipse would have in the x coordinate, you would have x is equal to a, and in the y coordinate, it would have y is equal to b. As we continue, these ellipses get larger, in both directions. Okay, so that's the z direction. Now let's think about one of the other directions. Let's think about the y direction for a second. So let's fix the y, move it to this side, then move this to the other side. So that would give us x over a squared minus z over c squared is equal to negative y over b squared plus 1. Yeah, okay. So now if we look at this, so there are a few things that we can do. We can move the 1 to the other side and take the square root of, and put the negative and take the square root, and we would get a hyperbola. So I'm not going to go in detail into, whenever you would have something like y is equal to the square root, sorry, this is going to be y0. Yeah, that's going to be y0. Right, so yeah, of x squared, let's say, minus 1 or plus or minus 1. And from this, we can read off different things about the graph. I'm not going to go too much into that. I would point out that if there isn't a constant over here, and you just had y squared is equal to x squared, then when you take the square root on both sides, they would cancel, and you would just get y is equal to x, which is a line. And we will see this in a second. But 1 second, I just need to get my charger because the battery. Are there any questions about this so far? Okay. Okay, so in general, when we have a hyperbola, we are, here's my x, my y, we have some lines over here, and so let's say it's going to be this line and this line. And these lines actually correspond to the situation where there isn't any constant over here. So then you're going to have the lines, and those are these two lines. And then this is going to be a hyperbola, something like that. So in our situation, our hyperbolas over here that come from these equations over here are going to look something like this, and like this. And you actually can figure out exactly where they go by knowing that at x is equal to a, it's going to hit the x-axis over here, and so on. So those are some hyperbolas, and then there are other hyperbolas coming in from the front to the back, so going like this and like this. And that would result, so, okay, let's just make sure. So when y is equal to 0, you get these red hyperbolas. So those come from this equation. And then when x is equal to 0, you get these hyperbolas. So that would come from setting x 0 over here. Okay, so let's go back to book. So these are the hyperbolas of one sheet. And that's when you have a +1 over here. And let's go quickly through what we just looked. So it would look something like this. Again, it has an hyperbola in the YZ direction. It has hyperbolas in the XZ direction. And it has ellipses in the XY direction. So there are ellipses, and those are the easiest to see. Okay. And they ask us to find traces of the hyperbola of one sheet. So again, when you're looking at this and you said Z0 over here, Z0, so that when this is 0, you just get an ellipse. So that would be this ellipse. And then when you move it, when you have the x0 on the other side, so this would be an hyperbola, and we would know exactly where it goes. It would go through the point, well, it would go through the point at 2 when at x is equal to 2, because here x is over 2, and so on. So it's fairly easy to look at this and turn it into a picture. Now let's look at the hyperbola of 2 sheet. The hyperbola of 2 sheet comes around when you have a negative 1 over here. And the reason for that is fairly straightforward. So if you have an equation x over a squared plus y over b squared is equal to z over c squared minus 1. Now this over here is positive, so this side is positive. This side might be negative at this point, because that if z over c squared minus 1 is less than 0, then this side is negative. At which point you cannot have a positive number equaling to a negative number, so you just won't have a solution. And this happens when z over c squared is less than 0. Sorry, less than 1. Which happens when z is less than c. Which makes sense. When z is less than c, this would be negative. Now, less than z or bigger, let's say equal to negative c. So in our graph, that would mean that from the point z is equal to negative c, so that's this point here, up until the point z is equal to c, that's this point over here, we will not have any solutions. So we start off by not having any solutions. And then after that, this gets the same characteristics as the first one. So in one direction, you have ellipses. So you would have an ellipse that would be growing. Notice in the other direction, you would have ellipses. And you would have these hyperbolas like this. And if we go back to 1 second. Okay, good. So that would end up looking like this. And that, like we said, from negative c to c, we do not have any solutions. So does this make sense? Hello? Hey, guys.
Yeah, it does.
Okay. Okay, so now they want us to show that this thing has no points between negative b and b. So that's basically exactly what we just did. For this example, we would want, this is positive. This over here is positive, and this over here is negative. So we would want y over b squared to not be less than or equal to 1. We would not want this to happen, which means that between negative b, y less than or equal to y less than or equal to b, we do not have any solutions. And that's between here and here. Okay. That's what we just did. And now they want us to look at the elliptic cone. So here's our elliptic cone. So the elliptic cone is actually fairly similar, and we're going to see why, to the hyperboloid plus, but it just does not have the constants. It just has this is equal to this with no constant 1. It's amazing how you would have such different shapes, but we'll see in a second why that comes out. Because, okay, so let's first write it. X over a squared plus y over b squared is equal to z over c squared. Okay, and here are our coordinates. X. Now, like before, in the z direction, we have ellipses. So when z is 0, we have a point, and then as z grows, we get ellipses. So the question is, what type of ellipses, how do those ellipses look? Like before, we also got ellipses in the z direction. So if we set, let's say, y is equal to 0 first, then we get x over a squared is equal to z over c squared. Take the square root, and we get cx is equal to zb. And this is a line in the xz plane, and it's a line that looks something like this. That one green. Here's that line. But because that this is squared, the negative line will also satisfy those equations. So that line. And then we can set x is equal to 0 and get y. So that would give us y over b squared is equal to z over c squared. So that would give us cy is equal to bz. We would get lines again, and this is in the yz plane, and these lines would look something like this. This would be one of them, and then this over here would be the other. Here are lines. And then if we add the fact that we had circles, well, we're going to get these circles. And that would give us a cone. Now, there are actually hyperbolas over here, because that if y, for example, is not 0, but we set it to be y0, then over here we're going to have minus y0 over b squared. And this is a hyperbola, and it would be somewhere, well, let's say over here you could have, so this is in the xz direction, so you could have an hyperbola right here like this. And it doesn't touch the line, so it would do what a hyperbola would do. But at the point you have lines. That's the point. When y is equal to 0, you have lines. So that's how we go from this cone to the hyperbola of one sheet that we saw before. And then if it's negative, this kind of gets detached and moves up a little, because that we cannot satisfy those points. So are there any questions about how these three shapes are connected? Is it clear?
Yes, please.
Okay. Second. Okay. Okay, let's continue. So here, that was the elliptic cone. And now, then they want us to know these last two surfaces, and that is basically it, I believe. Or maybe, yeah. Okay. So the first one is the surface Z is equal to, so let's look at that one. Okay. Z is equal to x over a squared plus y over b squared. And this over here, well, when z is different constants, we want, once again, we get different ellipses. So we would start at a point and get an ellipse and a bigger ellipse. Okay. And there is no z negative because this can't be negative because this side is positive. Now, if we have this 0, then we would get z. If the x is 0, z is equal to y over b squared. And so that is going to be, so here's my x, y, z direction. So in the y, z direction, you will have a parabola, because this is a parabola. Similarly, if I have z is equal to x over a squared, this is also going to be a parabola in the zx direction. So in the zx direction, we're going to have another parabola. And that's how that looks. So it's the elliptical paraboloid because it has the elliptical component of the ellipses that we saw, these ellipses. But then it has parabolas. Here are the parabolas. Okay. Now let's look at this one, the hyperbolic parabola. So now we're going to have z is equal to x squared over a minus y over b squared. So, okay. So now when z is a constant, then, well, let's try first thinking about the parabolas. So when my y is a constant, I have a parabola, right? So let's start with y is equal to 0, or in general, when we have z is equal to x over a squared minus y0 over b squared. Okay, these are parabolas with this interception. So as y gets bigger, these get smaller. The interception gets smaller. So we're going to have, let's say, so this is this parabola, and then we're going to have this parabola, and maybe this parabola. Actually, it's better for me to try to draw the picture first. So this is going to be a horse saddle. It's going to end up looking like a horseshoe. And it will look like have a parabola. One second. Okay, it's going to end up looking something like this. Okay. So now, like I said, in the x, so here's x, y, z direction. So in the x, z direction, you have these parabolas. And they look like this. And they gets smaller and smaller. So that over here are these. So it just continues going down. 1 second. Yeah, I have it kind of sloping back up, but it does just fall down. So those are these. That's what we just looked at. Those are those parabolas. Now, if we set our x to be 0, then we have, sorry, to be a constant, then we have z is equal to x 0 over a squared minus y over b squared, and this is also a parabola. Now the interception is getting bigger, but my parabola is negative. And these are going to be these parabolas over here. Well, let's do red, this parabola, and this parabola. As x0 gets bigger, they keep falling. In the book, there are these parabolas. Oh, sorry. It's not correct. Yeah, I just didn't draw this correctly. But anyway, there are these parabolas over here. This parabola, it's negative, and it increases in the x direction. As x increases and plus minus, they go up, but they're negative. So it would be parabolas that look like that. So let me try quickly to redraw this in a second. So once again, we have parabolas that come down. They go up, but they're coming down. And then they kind of go up again. And then we have other parabolas that come like this. Okay, won't be. Okay, again, not a great picture, but it is a little difficult. But anyway, this is how it's supposed to look. And then the last part is when my z is held constant. So when my z is held constant, and this is z0 is equal to x over a squared minus y over b squared. And these are hyperbolas. Because now you have that the z0 is constant. So each one of these is a hyperbola. And those hyperbolas appear here. So this is when z is equal to a constant, and there are these hyperbolas like that, and then you have another one here. So you have these hyperbolas like that, and this is in the z direction. Okay. They have an hyperbola, and then you have something like this. These are the parabolas, and this is how your saddle looks, basically. And again, these over here come about when you set y to be constant, and then the other parabolas, those come around when you set the x to be some constant, and then you have the negative parabolas that come about when you set the y to be a constant. Okay. So now they tell you to show that z is equal to xy is also a hyperbolic parabola by writing in these equations. So you just plug it in, you get that, and that is a hyperbolic parabola, the way we just saw. So not too hard. Then they ask you to determine what this surface is without looking at a formula. So x squared plus x squared plus 2z squared minus y squared is equal to 0. So they ask us to figure out what this surface is. And what we can do is first we can move this to the other side and we get some understanding of what this is going to look like. So we know it's of the form which is either a hyperboloid of one sheet, a hyperboloid of two sheets, or a cone, and it doesn't have a plus here, so it's probably a cone, but we can't really use that. So the first thing that we can try to do is we can try to set the z is equal to 0, and we get a line. X squared is equal to y squared, so we get a line. That's when z is so. Z, and when z is equal to 0, we get a line and another line because we're having squared. Okay. Now we can try to think about what happens when we set x is equal to 0, and that would give us a line in the zy direction. So that would be, or again, two lines because of the squared. So one line, two lines. And then whenever the y is set to be constant, one second, you get, yeah, so I'm not doing this. So one second. X, Y, oh no. Okay, let me just erase these lines for a second. Sorry. X squared minus. Okay, let's try this again. When you set z is equal to 0, you get a line in the x, y direction. So that would be a line like that. That was a mistake, and another line like that. And then when you set, that's when z is equal to 0. When you set x is equal to 0, you get a line, another line in the yz direction. So that's in the y's, yeah, so y, good, yeah. Like that. And then in the other thing, you get a cone. So then you would get circles like this. And that gives us a cone. Yeah, and these lines are not perfect, but let's try to redraw this quickly. So we have a line like this. We have another line like this. Then we have our ellipses like this. And then we have in the, so this happens when we set z is equal to 0, x, y, direction, and that looks like that, and like this, so they come out, and then another line that looks like this, and like that. Okay. Any questions about this? No? Is it clear? Yeah. Okay. Okay, let's continue. So over here, they just finish off by saying that here you have a cylinder. It extends it to infinity in the z direction because there is no z. And in the y direction, you just have ellipses. So you just have ellipses. Yeah, for some reason I can't write, but you have ellipses in the z direction. This is an elliptic cylinder, so you have ellipses. Sorry, so this you would have circles, and this would have ellipses. This would be in hyperbolic cylinder. You have the hyperbolic part in the y-x direction, but then you don't have a z component. So again, it extends to plus minus infinity. And this would be the parabolic cylinder. Again, you don't have a z direction, so it looks like parabola. and extends like that. So it's always good to figure out what a surface is by looking at, setting different things to be constant and trying to see what lower dimensional surfaces we get that we recognize. Okay, so now running the summary. Oh, sorry, my computer just rose a little. Good. So we have the ellipsoids, like we said, we have the hyperbola of one sheet, the hyperbola of two sheets, the paraboloid, which has parabolas and an elliptical part to it in the z direction, the hyperboloid, which has two parabola aspects to it and one hyperbolic part, the cone, which we talked about the lines that constructed, and the ellipses, the elliptical cylinder, and then these last three are fairly straightforward. Okay, any questions about any of these surfaces?
No.
Okay, so next time we're going to continue with vector valued functions, and we are going to stop here unless there are any other questions. So, if there are any other questions, please ask them. Otherwise, okay. So,
Hey, real quick, the class last Thursday's class, is that posted on your YouTube?
it's not, well, I just sent the class, so it's not something I did, so I didn't post it, but you have the link to it in,
Okay.
yeah, you have the link to it. Okay. Any other questions? Okay.
I was wondering, my friends in 230, and they had their teacher just set up their achieve assignments so they were the same day each week. I was wondering if that would be possible for our class, because I feel like it's hard to follow when they're going to be posted.
Oh, so you wanted the due date for them to be at the same time. Okay. So I could say that I'll try to make sure that it's just going to be Fridays. All the due dates will be on Friday. Okay.
Okay, thank you.
Any other questions? Okay.